Hi everyone, I'm Zhenya, and this is Ren.
Hi.
We are here today to tell you about a little experiment we ran over in the past 6 months as part of the innovation team at ARCore.
Thanks for coming along to our talk. Hopefully you walk away today a little bit inspired by our experiment and the possibilities of using ARCore to unlock problems we didn't even realize existed.
But before we get started, hands up who in the audience has heard of augmented reality? It's been all over media for the last year, so yeah, that should be all of you.
Alright, keep your hands up if you've tinkered with AR yourselves. Anybody? Excellent. And I don't suppose anyone's actually been lucky enough to ship something to the store with AR? No? Alright. Well, it's great to see that so many of you have gotten started playing around with it because we think that AR is about to get really exciting.
For those of you who watched the keynote for Google I/O this year, you should recognize this next section. Google has been putting a lot of work into their AR offerings, and they try to put AR into their own products. This is an example of how Google is trying to use AR to provide a more engaging and informative map experience.
You can see here that AR has a unique ability to provide information that's specific to what your users are looking at. This creates the potential for location-based experiences that get the point across more quickly and effectively. And here's another example of how Google could represent the same information in two different ways. One that's easily scannable, and one that's intimately tied to the user's environment.
If you want to see more examples of cool new stuff built on top of Google's AR framework, go and check their AR experiment page. There's a huge range of really interesting interactions that you can play with. So we're on the same page with augmented reality. Now, how many people here have lost their way in a shopping center, a car park, or a library in the last month?
Awesome. I'll include myself in that one, Zhenya. I'm as obstinate about asking for help as the next person. So if I'm searching for, say, pickles at the local IGA, I will have walked up and down 3 different aisles before finally surrendering and asking some overworked clerk for help finding the pickles I've just walked past 3 times.
Sounds embarrassing. But why are we talking about libraries and pickles?
Because, Zhenya, in most spaces, casual wayfinding stops at the door. Google Maps has done away with the days of asking strangers on the streets for directions or fiddling around with fold-out maps in your car. As a result, outdoor wayfinding is ubiquitous, accurate, and taken for granted. By comparison, indoor wayfinding is confusing, unreliable, and difficult to deploy.
So our team asked the question, what can we do about it? This is a story of how we tackle the indoor navigation problem with ARCore and stuff we had learned along the way. We built an Android app that takes away the confusion when you walk into a strange space. It recognizes where you are and guides you to your destination with intuitive AR markers.
And here it is. Great. So it's getting to the start of spring, and I don't know about all of you, but I get terrible hay fever. So here I am in the CBD down at the local chemist, looking for some hay fever tablets. I've opened up our app, and looking around has stabilized an understanding of the world around me. I've been told to go and find a poster, and I'm looking around, and I can see this person's face, which has been identified as something I need to look for. So I point the camera at it, and hey, a whole bunch of stuff has appeared in my world. I look down and there's a path in front of me, there's footprints on the floor, and give it a crack, I'm going to start following that. And after a few moments of ducking between other shoppers at the market, I find the aisle I'm looking for, I walk down and there's something flashing in front of me. Just to check, I go and kneel down, ducking, weaving, and hey, we've gone and found our hay fever tablets. So that was a lot to take in. Don't worry, we're going to break it all down, and you'll get a chance to review it in detail with us later on in our booth. So, are you all still with us?
Awesome, let's get started. During our talk today, we are going to explore the experience we had in creating the Wayfinder app. We will break down the problem and our solution, cover the tools we used to build it, and review the technical challenges we faced, and also discuss our approach in designing it.
But before we can dive into our solution, we need to set the scene a little. Here we are, lost, exploring our new sparkling office, loving life, and wishing we knew where that darn meeting room was. The first few weeks in our new space were a chaotic medley of interruptions as people wandered about asking for directions. But why did we choose to do something about this problem this time around, rather than for any of our previous moves? The answer is complicated, but the biggest factor was that the AR tools available to us have come a long way in the past year. Most notably amongst which was the stable release of ARCore. ARCore was released in beta preview late last year, and was officially released in February this year. It's the foundation of our work on Android, and is what enabled us to get started.
The ARCore framework enables smart devices to track users' motion through an understanding of visual feature points in the scene, using only a single camera. It also uses its tracking of these visual feature points, also referred to as point cloud, to establish an understanding of the vertical and horizontal planes in the environment.
These two features enable the placement of 3D content in a way that makes it seem to be a part of its environment, by resting it on real surfaces and scaling it as the user gets closer or further away.
But it wasn't until the image tracking capability became available in release 1.2 that we found the basis of our location permanence.
So what was our solution? We needed a way to map out a physical space in order to relocalize a user within that space so that we can provide them useful directions. The approach we took is broadly referred to as marker-based localization. Now, that's just a fancy way to express a very simple concept. The essence of it is this. We record the existence of an image in the environment. Then we record the positions of each other piece of digital content, such as destination markers or walkable pathways, relative to that image. Once the app detects the recorded image, we simply position the rest of the recorded content relative to it, and bam! We have a digital overlay that's mapped to real-world positions.
That all happened a little fast, so let's run a play-by-play. So we start off with recording the position of an anchor and a piece of AR content relative to a recorded frame of reference, its origin. Once we have recorded at least one anchor image, we are good to go. Our user opens the app in creating a new unknown position of the AR world, which put our AR world in the wrong position. So we encourage user to work towards the anchor image and allow the app to detect the anchor image and scan it. This allows us to calculate offset from the visual anchor to the detected anchor. And then we apply this offset to all other AR pieces and place them into physical world correctly.
It's worth noting that our user is just as capable of opening the app facing in a different direction as they are in a different position to the location record. We need to account for this rotational delta, along with the application of our positional offset. Otherwise, our content ends up misaligned. And now, since no technical talk would be complete without it, our solution diagram. There are two main flows to be aware of in our solution. The first one is our recording flow, in which we grab photo captures of the environment and tag them with pose data before uploading data and images both to our Firebase backend.
The second important flow in our solution is the detection flow. To kick things off, we download our location record, including our anchors and pose data. We then specify an anchor image to ARCore as image that need to be searched for. And once one of those images gets detected, we feed the detected pose into our localization algorithm. And we get calculated position and the rotation of delta to relocalize our AR world.
All right, so we've gone ahead and built an app that allows us to find our way indoors. But what actually went into building it?
We now know what the space looks like, and we've matched it to our map. It's time to get moving. We know how to align the virtual and physical world, so let's get to the fun part and start creating some 3D content.
ARCore can be used to create compelling interactions and experiences unlike any that we've yet become familiar with. But in order to achieve this,
we have to write this. For anyone unfamiliar with OpenGIS, this is the code that's doing the shadowing, positioning of our 3D models, or at least a part of it, a small part.
Understanding the OpenGL code well enough to make useful progress was a learning curve that took far too long to get ahead of. The skill set is unfamiliar to us as Android devs, and ideally we want to be doing as little actual math as possible. There has to be a better way. We needed some help.
And Vericore comes to rescue. There are plenty of smart developers who are keen to simplify things and share their work. Vericore is a product of VeraMedia and is designed to make the handling of 3D content in AR a breeze for regular developers like us.
Coming across Vericore was a miracle for us 6 months ago, and working with their SDK has been a fantastic experience so far. We've observed that the team behind Vericore is extremely responsive and quick to ship updates. Only 3 days after the 1.0 release of ARCore, they shipped their 1.4 version supporting it. Our team raised 2 issues and 2 feature requests with them across the course of our project, and all of our queries were addressed within a day and promptly shipped in their next release.
These models, by the way, come from a series of parallax puzzles we created for our brand review experience earlier this year. You can see that we achieved a similar effect to the one we implemented with ARCore, but with Vericore, the code required fits in a single slide. There's even more functionality represented here, because we have the ability to connect 3D content with parent-child node relationships.
Vericore was the tool that enabled us to start making real progress 6 months ago. But why are we still using a third-party framework? It seems that whenever the smart folks at Apple or Google come up with a new tool, the other one quickly follows suit. And this is great for us devs, but we could only wish they didn't insist on such confusing naming schemes. When Apple came out with their ML library for iOS, or ML, Google was quick to follow up with the release of MLKit through Firebase. When Apple came out with ARCore, Google responded by transitioning Project Tango into what we know as ARCore. And Apple's had this thing called SceneKit since 2012 on Mac and 2014 on iOS, which is their ability to go and manage 3D objects within a scene. But Google's been absent in this area up until recently when they broke the naming conventions and gave us Sceneform.
So finally, as of May this year, Google released the Android analog of SceneKit straight to public 1.0. Similar to Vericore, Sceneform provides a wrapper around OpenGL code and provides an API for parent-child node relationships. The functionalities they have available out of the box isn't as extensive as VeraMedia's more maturing offerings. But our initial look at it gives us a feeling that this is going to be a much more powerful API.
Our parallax poster example becomes even simpler to implement here, and comes with complex lighting and shadow effects out of the box. And here's the code. It's not a direct comparison to the previous Vericore example, but it is very elegant and powerful. The keen-eyed amongst you may have noticed that this code includes no mention of textures or materials, whereas our Vericore code included some custom texturing work. This is because our friends on the Sceneform team have decided to implement their own 3D model format that bundles in all of the texture information for us.
The Sceneform binary format and its corresponding human-readable Sceneform asset definition file acts as a wrapper around whatever 3D model that you choose to use, so long as it's an OBJ, FBX, or GLTF file. It's automatically generated by the Sceneform Android Studio plugin upon importing your models, and includes a collection of attributes that allow you to tweak its appearances.
Speaking of, one of the sweetest parts of using Sceneform is the Android Studio plugin they've supplied us with. It's still in beta, but it gives us easy asset importing flows, automatic Gradle dependency configuration, and this awesome asset viewer right in the IDE.
So to summarize, the stable release of ARCore in February allowed us to get started. The ARCore's more helpful abstraction enabled us to get moved. And Google's Sceneform is the future for developing AR in Android. As helpful as all of these tools, our path to implementation isn't a walk in the park. We faced plenty of technical challenges in building our indoor navigation solution, and we'd like to share a few of them.
We're well on our way, but before we arrive at our destination, we have a few roadblocks left to overcome. These are the hurdles we're struggling with today, and our attempts to surmount them.
The first problem we ran into wasn't some grand technical flaw. No, it was a fair bit closer to home. Who here regularly use ADB or Wi-Fi when developing? And it's terribly convenient even for developing regular apps. But as you can see here, it solved a huge issue for us, as the AR app that we're building requires us to actually get up and start walking around. So don't be like us, struggling with cables for the first few months of development. Use Wi-Fi debugging to build your AR app.
Something else we ran into as the app became more complex was that keeping the AR code well separated was becoming difficult. Look at this comparison of our 2D and 3D experiences. One advantage we don't realize we have in mobile development is that unless you're building an infinitely scrolling newsfeed, functionality on any one screen is naturally limited by what the user can handle all at once.
But not so with AR experiences. User naturally uncovers more functionality by walking around in their physical surroundings and adding content to their scene. AR views are potentially infinitely complex, all contained within one camera view. We need to come up with new abstraction in order to share behaviors across objects in the scene.
The remaining challenges we'd like to highlight are all related to the key part of our technical solution, image recognition. Not just any old image makes for a good image target. And the main physical limitation we have in navigating a space is how many high-quality ones we can either place or make use of. In order to ensure that our localization approach works well, our image anchors need to be recognizable, specifically by computer vision techniques. Conveniently here, modern computer vision works in a very similar fashion to the human eye, so anything that sticks out as a complex image tends to work just fine. Technically, we're looking for a high concentration of irregular feature points, which look like sharp corners of high contrast in a given image.
To be useful, an image tag needs to be unique, because if an anchor image is duplicated in an area, we wouldn't be able to know which the image user is pointing at. In this example, we contrasted a common and recurring wall panel with our uniquely styled poster. We can ensure there's only one poster that's in the area, but the wall panels present an issue.
Finally, our image targets also need to be stable, because we can't know that an anchor has moved ahead of time, and we have to assume that it's still in the position we recorded it at. If an anchor moves because it's on a door that swings on a hinge, then our mapping of the world will swing on that same hinge when we detect the image.
Our use of image tags don't come cheap. Each image record could take up as up to 5 megabytes in our database, which became popular when we have 15 of them. Scaling this solution was going to be difficult, but we are optimistic that there's a linear image recognition format available for us under the hood of ARCore.
Finally, we struggled to know that our anchor images were performing well, since we lacked a tool for quantitatively assessing them. Google has provided a script that programmatically assesses how recognizable an image is, but we found that this doesn't necessarily translate to how far away or what angles it's recognizable from.
We wanted to know in real time when an anchor stopped working, so we started working our own tooling and to measure and visualize the image detection. We've packed this for now, but look forward to seeing something new in the future. Alright, we've covered the big challenges faced on our journey. The next thing we want to examine is how to design an AR experience.
So here we are, inside of the finish line. As technically challenging as the project was, it also presented a huge design challenge. We realized early on that many of the affordances that we were used to in creating 2D apps didn't neatly apply to 3D experiences. Touch states, selection states, zooming, data refresh, motion, these commonly understood UX aspects of typical mobile apps just didn't translate well. So we needed to consider carefully our approach to designing for AR.
After some early failures, we come up with a set of guiding design values to ensure that we were on the right track. First, we promised to ourselves that whenever it comes to design a new interaction, we would ask ourselves, what would it look like in 3 dimensions? This helped to jolt us out of the familiar 2D paths and to force us to consider other possibilities. We know that the user suffers a cognitive overhead when they switch between the context of AR and the screen element, so we wanted to keep them immersed as much as possible.
Second, we quickly realized that we were making assumptions about the ways that our users would move with the app in their hands. Our first round of user testing was brutal. People just didn't understand what they were supposed to be doing. Working with AR every day meant that we had an intimate understanding of what interactions were possible in 3 dimensions and knew about nuances of motion and feedback within the scene that our users weren't. In order to avoid making unfounded assumptions and about user behavior, we resolved to test with new AR users as frequently as we could. We already knew that user testing was a good idea, but I would say that frequent validation is even more important for AR than it is for commonly understood 2D experiences.
Finally, we love to see the joy on the faces of our user when they experience AR for the first time. But that joy quickly disappeared when the users had to suspend their disbelief. If a virtual object that's in front of them does not look or behave like what they would in real life, user would suffer they would experience a mental disconnect that diminish our overall experience. Whether it was footprints appearing in the floating in the air or virtual objects that intersecting with physical world, we were alert for anything that broke the illusion of physical presence.
With those considerations in mind then, let's break down some of the interactions that we arrived at. We could go on for hours about individual nuances, but we wanted to focus today on 8 of the standout challenges we faced. The first challenge, how do we create a stable environment?
The first thing the user needs to do when they enter any AR context is to give the framework an understanding of their surroundings. With all these surroundings, 3D content is prone to drifting about. As you can see here, this clearly presents an issue for us.
To recap, ARCore maps the environment through the detection of visual feature points and an estimation of their distance from the user's camera. In order to triangulate this distance, physical motion is required. Rotation alone is insufficient. Google and Apple have both shared mock-ups of 2D animations that depict the kind of lateral motion that users need to undertake. And similar animations exist in a lot of AR apps, but these ones are provided out of the box for you to use when you're getting started.
Both tech giants has also attempted to address the need for feedback on the user's progress as they explore their surroundings. Google provides this plant detection indicator out of the box with Sceneform, whereas Apple has provided this multi-stage animation of a glyph that changes as the understanding of the environment improves.
And here's the interaction that we arrived at. You can see that we have our own visual that attaches itself to the ground plane and tracks the user's focus point. It's not ideal, however, as it fails to effectively encourage the user to do more than just rotate their device and doesn't provide any feedback on their progress. We're looking forward to exploring other options that are more effective.
With the environment now established, the next interaction we had to consider was the successful detection of our anchor image. Initially, we lacked a success indicator upon finding an anchor image, but we found that users were left in limbo, wondering if they could move on to the next step.
We attempted to address this lack by showing a flashing rectangle matching the shape of the target image, but we found that inaccuracies in the detection made it difficult to line up the edges to our satisfaction. Instead, we went for a neutral, centralized asset in order to have a greater tolerance for any offset in the image detection.
Once our users had successfully scanned an anchor, we need them to turn to face the path that has just appeared beside them. We run into a problem. How do we highlight off-screen content?
The biggest issue with our initial release was that once a user had found an anchor point, they just stood there waiting for something to happen. The phone is just a small window into a complex 3D world, and indicating to the user that they need to point that window in a particular direction is a tricky interaction.
Google have given us some guidance on this topic, suggesting that an arrow in the screen is an apt way to indicating off-screen content. But there are other subtler ways of communicating the presence of this content. For example, shadows beneath a floating object is a great way to getting a user to look up when there's something floating over their field of vision. Initially, we opt for a compass treatment at the bottom screen, attempting to be a minimap-like approach to indicating the presence of other content. This quickly fell flat in our user testing though, with no one refocusing on the screen long enough to even notice this compass had appeared.
Designers at Google had actually come up with a name for this effect, which they refer to as cognitive tunneling. Essentially the idea that once you're immersed in the scene, it's easy to miss screen space prompts. We found that putting a 3D arrow in the world in front of the user was a much more effective interaction, since it didn't require them to break their immersion. So we've now found a way to put our user on the right path. The next stumbling point we ran into was how do we maintain their immersion while they're on it?
When it came to UI controls, we attempt to keep the user interactions in AR as much as possible. But sometimes we need a consistent touchpoint for accessing a specific function. Apple has advised that the way a user holds their device is even more important to consider for AR experience. Specifically, they recommended designing primary interactions so that they can be used in a single-handed grip, since this affords the user a greater range of motion. Towards this end, we have kept our UI controls in the bottom half of the screen for easy access. Here you can see the control center for our recording experience, which allows the user to add in content into their recorded scene.
Google has provided us with some guidance here as well, highlighting the need to avoid surprising the user with full screen overlays. It's important to allow the user to maintain their immersion, so the AR scene should be its focus as much as possible. When presenting important concepts such as the ability to change destination, we elected to use the minimum amount of screen space possible and get out of the user's field of vision unless otherwise requested.
We now have a strategy for staying out of the user's way and allowing them to enjoy the AR experience. But how long are they actually enjoying it? We're concerned by observations that the user was abandoning the experience halfway through and had to ask ourselves, what's the best way to prevent fatigue?
Most of our users' time is spent walking to their destination, so we paid a lot of careful attention to the design of our path display. Our first attempts included floating lines at about waist height and arrows up at about head height. However, we ran into a piece of UX research that made us realize we had the wrong idea.
Researchers at Google have found that we are most comfortable when holding our phone at an angle of 30 degrees from the ground, which is about here. We are not used to holding our phones up for anything beyond taking pictures, and holding them upright for long periods of time becomes tiring quickly. In order to avoid exhausting our users, we elected to lock the path display to the floor beneath their feet, and enabling them to hold their phone and still see the way forward. The footprints we landed on feel like a natural and playful progression from there.
All right. Our users are now comfortably immersed and happily roaming our mapped location. But recording this location took some effort as well, conducted through the app in an AR recording experience. There's a bunch of 3D content that needs placing in the scene, so we had to ask ourselves how we were going to guide effective placement of that content.
When it comes to placing 3D objects, we had a couple of good options. Our initial goal was to emulate the drag and place transition from 2D to 3D in Google's AR stickers feature, but we found it difficult to match the interaction neatly without more framework support. Questions were arised when about dragging animation and where the object would be placed once they enter the 3D world.
Instead, we took a page out of Apple's design book. They've demonstrated a neat placement interaction in their AR preview function, hovering a translucent asset in front of the user before transitioning it into place on an available surface. We settled on this ghost placement approach as something that was easier to consistently communicate and implement.
So our recorded thing now has content, but no one's ever satisfied when in the first place they drop something. The next challenge we faced was how best to enable easy repositioning of the 3D content.
We decided that a drag interaction for our waypoints and destinations was vital in order to give our recording user fine-grained control of their positions. Google has some suggestions on this note. They recommend that we create a different state for objects that are in the process of being dragged and clearly display where those objects will land. They've also identified that in order to keep touch targets large and objects visible, they need to stay within arm's length of the user. You can see here an example of their recommended interaction, where the user is prevented from accidentally dragging an object off into the horizon, never to be seen again.
We implemented the maximum drag distance by displaying a ring around the user that follows them as they move. This ring indicates the area within which user can modify content, and if they attempt to drag something beyond the ring, they would be limited by a hard barrier. So now, our recording experience includes both content placement and repositioning. We've covered a huge variety of interactions so far, and many of them could get in the way of each other. So our final challenge was to consider how we were going to switch between the different modes of interactions.
We needed objects to be draggable, editable, deletable, resizable, linkable, and the list goes on. In order to have basic actions like clicking and dragging mean everything we needed them to, we had to establish a treatment for different contexts. We achieved this by having object-specific actions only available when they were in a selected state.
You can see here a great example from Google's AR design guidelines, showing off the selection interaction. How the bear is shown with a distinct outline and a surface underlay when it's selected, and how touching a space outside of it would result in a deselection. Unfortunately, this interaction requires a bit of customer implementation at this moment, but we were sure we were going to get some support in the future. For the time being, we went with a flashing version of stamp, allowing the user to see where their current focus is.
Alright, that about does it. We've come up with intuitive interactions to address each of the challenges that we ran into. Keep in mind that best practices for AR design are still evolving, and there are many more interactions that need fine-tuning and framework support.
And that's where you came in. AR is just barely emerging as a new medium, and there are still plenty of design snarls to unravel. We find challenges like how to indicate that content is clickable to be fun and exciting. The space is still wide open to be explored.
Here there be dragons, and this is your opportunity to go and slay some of them. Congratulations, you've made it through the bulk of our talk. We've covered the indoor wayfinding solution we built, how we built it, the technical challenges we faced, and our approach to designing it.
So where does all of that leave us?
If we want you to take away anything from this talk, it's that you need to treat 3D design as fundamentally different to 2D UI design.
The possibilities are endless and being explored further by bright people in the community every day.
Whether it's literally playing with perspective,
or sharing space together,
AR is the freedom to make something new.
And that's it for our talk. We got there in the end.